Hey, well, so in this video, I hope to do a handful of things. I'm going to try to summarize the last two videos you just watched on Khan Academy. I'm going to go through some more examples and actually show off how these questions look on AP level, AP calculus level questions, and then really try to hit on these two key points all throughout of why do we just look at the largest term, and how do we decide which part of the term or the expression of the function is doing a better job of racing towards infinity. And I'll answer those right now. So we look at the largest term because at really big values, that is the term that's going to have the most impact on where the y value, the output value goes to. So that's what we just worry about the largest term. I'm looking at this example right here. Well, if I'm wondering as I approach a super negative big number, which just for context, like infinity is a concept. The world is only, it's less than 14 billion years old, and the earth as we know it has only existed for like 4.5 billion years. And we're talking about values that are trillions, quadrillions, quintillions, like that's what infinity is it's a concept of a huge number we really can't grasp. So the idea is, yeah, if I'm approaching like -5, then all these terms are going to have an impact on that in value. If this was the limit as x approaches -5, then we'd have to consider all these values because they would determine the output value. But at values of negative, huge, negative so hard, like such a large value, it's almost hard to comprehend. These other two terms are just not making the same impact that this first term is. This is going to drive the value so that we don't need to consider these other values. They're just not as impactful. And that kind of goes into like when we're racing towards infinity, which one's driving that race of that function towards infinity are the ones that we can pair. And that also goes into when we know that limits will go to 0 at large values. Why is that? How does one denominator outrace the numerator to get to infinity to let us know that the limit will be 0? So I'll hit on those two key points all throughout. But let's start with just basic polynomials. If you have a polynomial, your method to evaluate the limit is just going to be to consider function notation of large values. And so in this case, the limit's going to be as x approaches positive or negative infinity is going to be positive or negative infinity. We have these 5 examples. So when I look at these, I know that this function as x approaches super big number is going to be a super big number in infinity. And the idea is I really could consider in my head, 100 million, 100 billion. If I plug in more and more numbers to x that are large, I know that eventually I just get to a super large outcome. In this function right here, again, I'm approaching super large x values, a limit as x approaches infinity of this function, and I'm saying it's negative infinity for a few reasons. One, when I'm looking at this, I'm ignoring, I can actually cross off to show you how much I'm ignoring them. I'm ignoring, should have set my timer, these other two terms at the very end of the function. So these don't play in at all to me. I'm just analyzing this right here. And then I'm wondering, okay, if I actually input a very large value, I'm thinking in my head it's a super big positive number. Well, this is saying square that. So like a super big positive number times itself just results in a super big positive number. But then we have this, gargantuan positive value times a negative value, and we still follow our same rules of math where a negative times a positive results in a negative. And so this function approaches negative infinity. And then we'll see when we graph it, this is just a negative quadratic, so it's going to be facing downward. So as we approach super big negative x values, well, the y value follows suit and goes to a super big negative y value. For this next example, we're saying as x approaches negative infinity of this function right here. Like I said before, I'm not considering these other terms, even though they would affect the outcome at smaller x values. This is the only term I have to compare. And then similar to how we just compared this quadratic, I'm imagining I'm plugging in a super big negative x value into x. And so I have a big negative times a big negative times a big negative times another big negative, which results in just a gargantuan positive value. But then our same rules of math still apply. A gargantuan positive value still times a negative results in a negative outcome. And that this function right here is a cubic with a negative coefficient. So they're like quadratics, but they're even more like extreme. Like they're very straight up and down. And this function, as we got to really big negative x values, would just dive towards negative infinity. And then just a reminder, if I have a 5, all these functions I could write with y equals to like make them remind you that they are just functions. I could say y is equal to all of these. And so when you're seeing just a number, please remind yourselves that's just a horizontal line. So whatever the function is, it's the line, in this case, y equals 5. So no matter if I'm going off to positive big number or negative big number, that output's always going to be just 5. So if you see a number, don't get confused by it. It's just a constant function with a constant value. I'm going to clear all that and move down the page. So now we're looking at rational functions with matching exponential terms. What I'm trying to say is whenever you have a rational function, so a polynomial in the numerator and also the denominator that have the same largest exponential term, the way you actually find that limit is you compare the coefficients of those values. That's what I have set up here. I thought it was pretty good math language. So if I have a function with a numerator and denominator, like a number in front, that was what I was going for, was coefficient, and I'm saying x to the same exponent in both the numerator and the denominator. So I have some value to the same exponent in both top and bottom. The limit's going to go to whatever that coefficient value is. So we can see that, and actually I'm going to pause. All right, cool. I wanted to show off some Desmos stuff, and I'll do that for both of these in a second. But I can see for this function right here, when I'm trying to figure out this limit as it goes to positive or negative infinity, doesn't matter. I'm just analyzing and comparing these two functions, not because they're in front, it's because they have the largest exponents, x to the fourth and x to the fourth. And then if I keep racing to infinity, they're gonna have roughly the same race. They're gonna like race at the same speed, which is not a real thing, but that's the idea I think about, is like they're gonna race at the same rate. And so when it comes down to it, the x over 4s and x over 4s, if we actually rewrote the limit as x approaches positive or negative infinity, because with this setup, it doesn't matter, they're gonna approach the same horizontal asymptote. If I compared 2x to the fourth over negative 5x to the fourth, I could even act like I'm simplifying, and I'm just comparing essentially a constant function. Where's the limit gonna go of just the coefficient negative 2/5? And that's the same thing you all did in your summer homework with end behavior. It's an end behavior look. And then same thing here. And one thing I tried to maybe sort of trick you with in the bottom one was if you looked at these two terms, you might say, oh, it's gonna approach 0 where y equals 0 for a horizontal asymptote. That's not true, because I should ignore these terms and look at the biggest term. And when I compare those two terms, then the coefficients are just 1 and 2. So this goes to 1/2. So now I wanted to show you, if I can, my Desmos graphs I had set up. This is for question 1, and I should erase all that annotation because it's in the way clear on my drawings. We can see really quickly, this was the first function. Again, just y equals 5x minus 1. Here's our y-intercept at -1. It goes up 5 over 1. So you can see 1/4 is on there. As I go to really big x values, you can see it just takes off north. It takes off the super positive y values. We can see this was the upside down quadratic. So let me go the other way. So we can see it's a downward facing quadratic. So if I'm going to negative infinity, I'm referring back to example 1 problems now. If I go off to negative big x values, again, I'm only at -3 and some change. I'm already at -48. If I keep going down this, I'm at almost -8. I'm already at -353. If I keep following that pattern, I'm going to eventually get to negative infinity for the y value. And like I said, quadratics, or rather quartic functions to the 4th power, are just like quadratics where they're facing up or down. They're just a more extreme, like they're getting to values faster. So let me zoom in a little bit to get how it looks. See, it's basically like a parabola looking. It does have these kind of cool shapes in between, which we'll get into this year. But then as I get to, negative values, big negative values of x, I'm still positive for a while. But then as I get to negative, I'm almost at -4, I'm at -350. And then again, for the constant function, just a reminder, that's just a constant line at y equals that value. And no matter if I travel to super big negative x values or super big positive x values, I'm going to get to y is always 5 on that function. And then I'm going to shift over here to the functions we just analyzed. So here's the first function we just analyzed. We can see it's a very interesting function. It's got these, it looks like vertical asymptotes at x equals whatever would make this whole denominator 0. And then we could see that as I approach really big positive x values, it looks like this function is going to get closer and closer to where y is -0.4, which is -2/5, but it's never going to quite reach there. And then I can also see same thing as I get to really big negative x values. It's trying to creep towards -0.4, but it's never going to reach there. One thing I find out that I'll show you right now, if you write in Desmos and function notation, then what you can do is just plug in really big values. So I'll say f of, and I'll start adding zeros, simulating a super big value. You can see after even just, we got to 10,000, it's like, yeah, you're gonna go to -4. And no matter how many zeros I add, it's like, yep, eventually you'll get to -4. Like, trust me, you're gonna get there. I can do the same thing for big negative values, go away, of the same function. So I can say, I didn't want to do that at all. f of, and I'll say -10, and you can see start to creep towards -0.4, and eventually it just like, okay, that's where it's going to go. Let's call it there. And then same thing for the function we just saw. If I'm comparing, again, the terms t to the third, which I'm trying to highlight, and then 2t to the third, if I compare those, you can see it actually does a really fascinating function. It's like not a quadratic. There's definitely a name for this, but I don't know it off the top of my head. You can see as I start to go to big x values, getting really close to 0.5, which is 1/2, and then same for big negative x values. And that's because when we have the same sort of matching exponential term, we can know about functions. Okay, I'm going to approach the coefficients of those leading terms at positive and negative infinity. And again, just for fun, I can enter just big values, and eventually it'll say, yep, you're almost at 0.5, and we'll call it then. And I can do the same thing for big negative values. You can see how if we just plug in just to see, yep, it gets there, it gets there, it gets there. Yeah, we get it. It gets the big negative values, okay? Reminder or preview, we'll have a lot of g of t, f of t. A lot of functions later on in calculus actually analyze movements of particles with respect to time as your input. So get used to seeing like t values, because that's really a better way to consider like x values, input values. We like to analyze functions over time. Let me go back to my notes. So now if we have a rational function scenario where there's a larger exponential term in the denominator, the method is the limit's going to go to 0 every time. So if you have this setup where you're comparing the two biggest terms and the exponent of the bottom term is greater than the exponent in the numerator, the limit's going to go to 0. I think that makes sense. This goes back to the idea of racing towards infinity. So if I'm comparing, this function, it doesn't matter if I'm going off to positive or negative, it's t, so let's actually have time approach. Isn't that a cool concept? Time approaching positive or negative forever. And then I'm comparing these two leading terms of t squared over 2t to the fourth. If I plugged in 1, I can get a comparison value. That's just 1/2. If I plug in 2, I have I'm already at 4 over 32, so 1/8. But the idea is like this is just going to race toward infinity at just not as fast a rate as t 2t to the fourth. And so we say eventually there's just like, it's some numerical value, but over just such a bigger value, we're like, it's almost negligible. So we just call it 0 in the end. And you can see that actually play out. If I go back to clear this, clear all drawings, go to my Desmos graphs, you can see that like that does play out. So here's the first function we just analyzed. You can see, again, very fascinating function, right? I zoom out, looks very cool. I zoom in, you can see that if I go off to positive infinity, it gets really close to 0. If I go off to negative infinity, eventually it'll go to 0. Again, limits at other values. This same function, if I had the limit as x approaches -1, well, it looks like we could get there. As I approach -1 from the left side, looks like I'm getting closer and closer toward 3.1. I go from the right side, approaching -1, same value. These are just trying to analyze functions as they approach in behavior huge values. So keep in mind, a single function has tons of different limits depending on what value you're approaching. But for this situation, as I approach infinity, positive or negative, and I have a bigger exponential term in the denominator compared to the numerator, yep, I'm going to approach 0. And then this is the last one. I'll flip back to my notes real quick. If you have a scenario where the numerator of the rational functions is greater than the numerator and the denominator, you're going to have a function go off to positive or negative infinity. But it's going to depend. I want to make that point really clear. So we kind of start with the same analysis. Let's look at this first one. As x approaches, or z rather, approaches positive infinity. Well, I'm going to, again, just compare the biggest terms for the reasons we talked about. And then I'm going to say, okay, the limit as z is our input this time, as that approaches a big positive number, comparing z to the 5th, compared to 2z to the 4th power. Same idea of, okay, this is, if I, to the 5th power, a big number, I have a huge positive number. 2 big values to the 4th is, again, a huge positive number, but it's definitely not 1 because it goes back to this just races there faster. So we say that this infinity, it gets there faster, it has a bigger say, and so we just say, all right, it's going to be positive infinity. But a really big key point to hit is, if I'm comparing this going to negative infinity, it does change the outcome. Again, for our rules about how values, like still like our math truths about multiplying positives and negatives. So if I compare this, what I'm essentially going to say is, all right, if I take a huge number and raise it to the 5th power, That's a negative times a negative times a negative times a negative times a fifth negative, which results in a super big negative number. And this will be a super big positive number, but it's not like -1. Again, this outraces the denominator. So we say this approaches negative infinity for the reason as if I multiply a number, it's negative by 5 times, you get to a big negative number. And I'll show off this function too, just so you can see it in action. So again, if we look at the Desmos graph here, that is the wrong one. It's this one, yay. So if I look at this function right here, as I approach super big positive values, you can see it take off on that, almost like look like a straight line for a while. And then on the flip side, if I approach super big negative values, it goes to negative infinity. And again, we could check that real quick by saying, all right, let's just type in a bunch of numbers, and it gets really huge number in a hurry. So as I approach positive infinity, it approaches, again, positive infinity for y values. If I take the same k function, just typing in big negative numbers, looks like it takes off to a huge negative number, which eventually say, all right, it'll reach positive or negative infinity eventually. All right, for this last part of the video, I just want to show off how this information gets applied on the AP test and how some AP questions look and are asked. So move it down, there we go, nice. So this question is saying, which of the following pairs of functions, f and g, is the limits as again, that's showing a rational function. The limit as x approaches infinity, if I had those functions dividing each other, the limit of those functions dividing would be infinite. It's kind of a clever way of saying, okay, which two function pairs would the limit as x goes to infinity be infinity? And so knowing our knowledge of how we compare rational functions as their limits go to positive and negative infinity, we can find the right pair. So I'm not going to write all these out. You can imagine, I'll write the first one out because it's kind of important to show. So what I'm really saying is I wonder, as the limit goes to positive infinity, as x approaches positive infinity of x squared plus 2x, which is the f of x function here, compared to x squared plus natural log of x, pretty easy one. We're not going to worry about those two terms. If I divide those, I get 1, and the leading coefficient is just 1. So this limit would go to 1, which is not infinite, so I cross off a. And I just kind of keep going with this analysis. If I took f of x over g of x, well, I have a larger exponential term in the denominator. So this limit would go to 0. So that's not what I'm looking for here. This is an interesting one. It's testing your knowledge of exponential functions. But if I had the limit as x goes to positive infinity of 3 to the x compared to x to the third, well, this is going to outrace the denominator, because if we have a base raised to an infinite number of times in itself, it's going to get to infinity faster than x to the third. If you don't believe me, I would plug in 1 and 2 and 3 and 4, and you'll see pretty quickly, oh, this gets bigger faster. So this is our infinite limit. So our answer here is going to be C. This limit, if I compare just 3e to the x and 2e to the x, again, the e to the x is essentially cancel because they have the same exponential term. That limit would go to 3 over 2. And then this one, I had to actually test myself, but this limit goes to 1, and I don't know totally why. I will show you because it is fascinating. I'm going to clear. I'm going to show off my Desmos for 1 last time, then I'm done with Desmos for this video. And then you can see if I actually compare those functions, yeah, it gets to 1. I never get there as x goes to positive infinity. I get closer and closer to 1, and I don't know why that is. So if you do, please let me know. I'm super curious to know why, and I'll nerd around with it too. But let's look at another AP question. So this one, great question. The graph of which of the following functions has exactly one horizontal asymptote and no vertical asymptotes? So what that's saying, with our calculus knowledge, is it's wondering, okay, which of these functions has, as the limit of x approaches a big positive negative number, which of these functions approaches one limit? So I'm really wondering if it just approaches one horizontal asymptote. That's a scenario where you have, it's supposed to be an n. It's definitely, I can't even. It's supposed to be some coefficient value with x to the same exponent, and then some denominator value with x to the same exponent. We're looking for that because we know that this setup produces one horizontal asymptote, and we're looking for no vertical asymptote. So it means that the denominator, I don't know why I'm going to highlight, the denominator of all these functions has to be defined like it can't equal 0 ever, because that's where we get our vertical asymptote. So I'm actually going to analyze that part first. If I can see any functions in which the denominator would equal 0, I know it's going to produce, unless there's a removal discontinuity, it will produce a vertical asymptote. So I want to see if I can cross some of those out. So that's good, because no matter what x value I get, the squaring it will make it positive. And so this denominator will never be 0. If I plug in -1, however, to b, -1 to the third is -1, and so this would equal 0, so I'd have a vertical asymptote at x equals -1, and I need to find a graph that has no vertical asymptote, so b is out. C is interesting because if I had e to the 0, that also equals 1. 1 minus 1 would be 0. And so this would have a vertical asymptote where x equals 0. And I want to find the function that has no vertical asymptotes. But D and A, those are still good because I can plug in any values for e to the x, and this denominator would not turn to 0. So now I'm analyzing our in behavior stuff of limits. So I want to change colors because I want to. And I'm wondering the limits as x goes to, I'm going to consider positive and negative infinity. I could write them out as separate ones, but I don't want to, of 1 over x squared plus 1. Well, this is a pretty classic example where the denominator is going to dwarf the numerator. So this one would go to 0. So that's a good sign because this would just give us one horizontal asymptote at y equals 0. Whereas this right here, it's really interesting. As I approach the limits as x approaches infinity of the function 1 over, that is supposed to say infinity. Oh, goodness me. Infinity of 1 over e to the x plus 1. Well, if I plugged in a super big positive number right there, again, this denominator would dwarf the numerator. So this would go to 0. So right now it's like, I don't know if it's A or D. But if I plug in as the limit goes to negative infinity of 1 over e to the x plus 1, it's really interesting because e to the negative infinity, if we think about that, I'm trying to think of the right way to frame that. I'm glad I paused because I got the right way to explain it now. So if I had that going to super big negative values, what essentially is happening is, well, imagine I had e to the negative infinity. Again, if we raise anything to a negative exponent, we can rewrite that as 1 over e to the positive infinity. Those are mathematically the same. So what's happening is that this function right here, 1 over a huge number, would just become 0. And then as this function approaches big negative values, it actually approaches 1 as a horizontal asymptote. And so we would have 2 horizontal asymptotes for that function. We just wanted 1, so boom, has to be function A. For this last one, I did some pre-work to set it up right. So this question is asking, it's saying the continuous function f is positive, and I should have actually analyzed that better. So I'm glad I checked myself before I just lied to you all. So I got a big hint in the opening sentence. This is a very classic AP test where they give you big hints in little amounts of words. So this says the function is continuous, which we just know means it has no discontinuities. The continuous function f is positive. So it told me that right away, and I'll get to that in a second. It's saying it has a domain of x is greater than 0, and then it's saying if the asymptotes of the graph of f are x equals 0 and y equals 2, which of the following statements must be true? So what I tried to do is set up scenarios where, like, okay, if I followed that saying, okay, I don't know what f looks like, but if I followed that rubric of it has to be x values greater than 0, and they have to have a vertical asymptote at x equals 0 and a horizontal one at y equals 2. I tried to create some functions that we could analyze to figure this out. Now, right away, I should have read carefully that f is positive because as I started drawing these values, f is positive just means like all y values are positive. And so based on my scenarios, only this graph could actually be a good representation of this function because all these y values are positive. It's clearly approaching where y is equal to 2. It's approaching that horizontal asymptote, and it doesn't start until x values are greater than 0. And so we actually have a pretty good idea of what f, now f could be something like this, where it starts to oscillate up and down and then goes to where y equals 2. But we know that it has to be something like this, and knowing how it has to look, we actually can answer this question pretty quickly. Saying the limit as x approaches 0 from the right goes off to positive infinity. Well, that's true. We get closer and closer to x is 0, it does go off to positive infinity. And then as x approaches 2 of the function f of x, it goes off to infinity. So A looks pretty good. I'm still going to look at the rest really quickly. As x goes to 0 from the right side, and now it goes off so we can see from our graph positive infinity. So B is wrong. As we approach 0 from the right side, yep, it goes off to positive infinity. As we go off to infinity, oh, I'm really glad I read all of them because I made a silly mistake that hopefully you all caught. This should have said as x approaches 2 would be like right here. Like that's where x approaches 2. And that could be any y value, but it's not infinity, so that's crazy. So A is also wrong, but C is saying as x approaches 0 from the right side, it looks like our function does go off to positive infinity. And then as I approach, x approaches infinity, so it goes off to really big x values. Yep, we have a horizontal asymptote right where y equals 2. So C is our answer. And this, nah, it's approaching 2 and saying infinity. That's just mixing stuff up. So again, if we read carefully, we can recreate a situation that matches what this question is going for, and then just kind of reason our way through. And then very last one, I gotta stop hitting that, clear all of those. Last thing I'm doing for this video, very last thing, is just an alternative method for how we analyze limits. We can always do that sort of end behavior where we consider the biggest terms in both the numerator and denominator, but that's kind of a bit of a choppy way to analyze. A lot cleaner way to analyze where limits go to is to actually factor out the largest term. So you'll see this on Paul's online notes, and I really like this way to analyze this limit. But what I could do is notice that, okay, t to the fourth is the largest exponential term in this entire function. So I'm gonna factor out everything. I'm gonna factor t to the fourth out of everything. So I'm going to factor it out of the numerator and also the denominator, and then ask myself, if I factor out t to the fourth, what's left in this term to make an equivalent expression? What's really interesting, this would have to be 1 over t squared. So if I multiplied back through, I'd have t to the fourth divided by t squared, which would result in that t squared. And then I'm essentially dividing each term by t to the fourth. If I did that, I'd be left with 5 over t to the third. And again, your check is if I multiply back through, I'd have 5t to the fourth divided by t to the third, which will result in a negative 5t. And then if I essentially divided by t to the fourth, I'd be left with 9 over t to the fourth. Again, you consider factoring, taking out of each term or kind of dividing by each term. And then in the denominator, I'd be left with 2 for the first term, and then plus 3 over t. You might be wondering, Mr. Riggs, why are you doing that? And here's why. If I factored out, you cannot cancel individual terms, but you can cancel factors. So now these two, I've written one. This right here is a mathematically equivalent expression to the original expression. They are the exact same. And now that I have factors, I can cancel those. So what I'm really now doing is analyzing the limits as t approaches, and you don't approach the same positive and negative infinity, I'm just doing it for shorthand, of this function 1 over t squared minus 5 over t to the third minus 9 over t to the fourth, and then all divided by 2 plus 3 over t. I'll make sure I didn't make a mistake, so I feel like right now I did. Yeah, I got it. So from here, it makes it a little clearer of why this limit goes to 0. Because imagine I plugged in a super big positive negative number into all of these fractions. The idea is I have 1 divided by a giant number. So it means that that's just going to go to 0. I have negative 5 divided by a giant number. So now I'm subtracting 0. And I have negative 9 over t to the fourth. So I have negative 9 being divided by a giant number. So all those values just go to 0. And I have 2 plus 3 divided by a giant number, which if I'm dividing 3 by a huge number, that's going to be some so small decimal value, I just call it 0. So eventually I just have 0 divided by 2, and this limit goes to 0. So this is a more technical way to argue about what a limit goes to by factoring out the largest term you see. This might be helpful for the next objective. All right, hit me with your questions. I'm here for you, and I will see you next time.